Hello, in this video I'll be talking about the RMS voltages and currents. RMS stands for root mean square. This should sound familiar to you because in the topic of thermal physics, we have already discussed the root mean square speed of air molecules. For example, if you have 5 air molecules with these velocities, then the average velocity turns out to be 0. But the mean square velocity is 2. So to calculate the mean square, you got to square all the speeds before you take the average. From the mean square value, how do you calculate the root mean square value? You simply take the square root of the mean square value. So it turns out the root mean square speed is 1.4 meter per second. Why do we bother to calculate the root mean square speed? Well, it turns out that it's a very useful quantity because it's directly related to the average Ke of the air molecules, and it's also directly related to the pressure of a gas. So in the topic of alternating current, we are going to revisit this idea of root mean square value. But instead of averaging over a number of air molecules, this time we're averaging a waveform over a duration of time. So take for example this sinusoidal voltage with a peak voltage of 3 volts. What is the average voltage values? It's just 0, isn't it? It's a perfect sinusoidal waveform. Sometimes it's positive, sometimes it's negative, but over one period, the average value is exactly 0. But this is the mean voltage value. What we want is the mean voltage square value. So how does V square vary with time? When V is 0, V square is of course 0. When V is 3, V square is of course 9. When V is 0, it will be back to 0. When V is negative 3, we are back to the same positive 9. And then when V is 0, we'll be back to 0 again. So how does the waveform look like? It will look like this. The V square value itself is also a very sexy sinusoidal curve. So make sure you draw it with a flat gradient here, here, and here, instead of the humpy McDonald's sign, yeah? And this waveform peaks at 9V square. 9V square coming from the square of 3 volts. So the V square values is not constant over time. What is its average value? Does it look like the average value is 4.5? Yeah, it is. So there's no need to integrate and whatever. Just by seeing, we can tell that the average of this waveform is 4.5, right? Because the average of 0 and 9 is 4.5. The average of this point and this point is 4.5. The average of this point and this point is 4.5. The average of this point and this point is 4.5. So the average value for this segment is 4.5. And therefore the average value for this waveform is 4.5. So let me write it down here. The mean square voltage. See, remember, we square the voltage before we average it. So the mean square voltage is 4.5 V square. From the mean square value, how do we get the root mean square value? We take the square root of it. So it turns out the root mean square voltage is 2.1 volts. So a sinusoidal voltage with peak voltage of 3 volts has a root mean square voltage of 2.1 volts. How do we arrive at 2.1 volts? It's actually the peak voltage divided by root 2. So in general, for a sinusoidal voltage, the root mean square voltage can be calculated simply by dividing the peak voltage by root 2. So we are very lucky that our main supply is providing us with sinusoidal voltages and currents, because for sinusoidal waveforms, the root mean square values is very straightforward. Just take the peak value divided by root 2. So why do we bother to calculate the root mean square values? I'll talk about that in the next video. That's all. Ta-ta!